And Justin, you're up.
All right. Thanks, Gary, for the introduction. So I'll be talking, kind of about three different main components here, as I head throughout my talk. The first is going to be focusing on, just general, where we're at in terms of Massachusetts renewable energy goals for offshore wind, going to construction updates, both in southern New England and the lease, what the current status of the lease areas and wind energy areas are in the Gulf of Maine. And then I'll be going into, some fish and fisheries interactions, going into fisheries mitigation programs that are currently underway, talk about, trade-offs of those, then go into, what we've learned from both some lab and field studies in terms of different kind of, potential byproducts of offshore wind development and operation on fisheries behavior, as well as, fisheries resources. And then lastly, finish off with, just going to have an overview of the Gulf of Maine wind planning efforts, understand where we're at in terms of lease sales in the Gulf of Maine, and going into a little bit about floating offshore wind technology. So I just first wanted to provide an overview of the offshore wind goals within Massachusetts. Pictured here on the right-hand side, you can see a lot of the southern New England wind development areas in relation to what was the first offshore wind farm in the U.S., Block Island Wind Farm. It is that dot in that left, that blue dot off of Long Island, Block Island area. These names have changed over time. They continue to change. So it's just based on, differences in, which company kind of oversees those projects, and that influences the name changes. But overall, the Gulf of Maine has a target from Massachusetts of trying to achieve 10 gigawatts of procurement from floating offshore wind energy alone. The current statutory authority for Massachusetts, this was mandated by law, is to try to get 5.6 gigawatts of offshore wind energy by 2027. Currently, we are at around 3,500 megawatts procured. Gigawatts procured, that should say gigawatts, sorry. The EEA Interagency Council has an offshore wind strategic plan that aims to identify key gaps, needs, and findings. This is a new kind of plan that has been unfolding over the last year or so. So we partner with all EEA agencies, such as the Coastal Zone Management Office, Department of Energy, things of that sort. And there's three different kind of goals and objectives, themes that we're trying to achieve. One is having goals and objectives to socio-environmental and marine use needs, which includes fisheries and environmental impacts. The other is workforce and infrastructure development, as well as procurement and energy needs. So those are the three branches of where we're trying to bin different 2040 goals and objectives to try to balance, energy needs with also user needs and potential implications there. So, where we're at in terms of offshore wind infrastructure, offshore wind is, individual turbine is actually pretty large already, but there's efforts underway by a lot of engineering firms to grow the size of these different turbines. So pictured here on the upper left, I have a GE model of a wind turbine that's currently common in the southern New England wind energy areas. It's a 12 megawatt turbine. When you include the tower height as well as the rotor diameter, these are approaching 853 feet, which is almost getting to the level of, let's say, like the Eiffel Tower or the Chrysler Building you can see on these landmarks. And there's actually efforts, as I mentioned, by engineering firms to potentially introduce 15 to 20 megawatt wind turbines, which would produce over heights of around over 1,000 feet, and when you include the entire tower and blade height. And there's also different components that are important for procuring energy, such as the nacelle. This is the main kind of bread and butter of where the energy is generated. It connects to the hub of the blades, or the blades connect to the hub on the nacelle, and there's a gearbox and generator in that. So that's where the energy is obtained. And these nacelles are huge. They are 727 tons alone, and they're lifted, hundreds of feet above the surface of the ocean. So the expected operation of each individual turbine at this current point in time is 25 years. And in the US and in southern New England, they're currently spaced by one nautical mile apart. Some fishermen say this is okay, some do not. Some say it's too close together. So these are some concerns in terms of the spacing may not be adequate for some fisheries, potentially even those mobile gear or HMS recreational sought after species. So I also want to provide an overview of the entire kind of infrastructure that goes into offshore wind development for those of you that are unfamiliar. So as I mentioned in the previous slide, you have each individual wind turbine generator that produces its own energy. And there's commonly a foundation. The most common one in the southern New England region so far that has been installed is this monopile foundation. As you can see pictured here, that's installed around 65 meters below the sediment surface. And then there's interarray cables that are then attached internally into the wind turbine tower, so that where the energy transfer occurs. And then you also have these components known as offshore wind substations, which centralize a lot of the interarray cables, help stabilize the high voltage from the cumulative generation of all these different wind turbines from one wind farm. And then you also have an export cable, which is around 1 foot in diameter that is then also buried under the sediment surface, similar to those interarray cables. The target burial of these cables is around 6 feet to avoid potential conflict with different marine users, particularly draggers and dredges, like surf clam dredges and things of that sort. However, it's not always possible. I'll get into that in the next few slides. But once you get that export power on land, then it goes into a switching station. Sometimes we have what is known as direct currents that need to be switched to alternating current on land for energy generation. And there's current efforts to potentially have some storage capacities on land as well from offshore wind energy. I just want to focus on one aspect of the monopile installation. I'm going to be kind of breaking down different kind of components that go into the laying of these cables, as well as the installation of these monopiles. And here on the left-hand side is a pretty detailed schematic of what goes into the offshore wind turbine monopile foundation. You typically have a base of a monopile that approaches 39 feet in diameter. You also have what is known as scour protection, which is usually some type of hard structure such as rock or rock bags that can comprise roughly a diameter of 1 acre in area around a turbine. This is to reduce erosion, prevent erosion. And then you have what is known as a transition piece in this yellow, which transitions and joints the tower to the foundation of the monopile, or the monopile foundation. And this is actually one of the most noisy parts of construction is the installation of this monopile. So you can see here, based on this kind of rows plot, this shows you the decibel level with distance from the wind turbine installation, the monopile installation. You can approach decibels up to 170 or higher within about 5 to 10 kilometers of that radius, which, based on this chart here on the right-hand side, this can approach threshold levels beyond a pneumatic drill for decibel levels. So it is one of the most noise-intensive types of construction and pieces or components that go into offshore wind development. But there's currently some mitigation efforts, such as what is known as installation of a double-ringed, like, acoustic bubble curtain to attenuate those decibel levels within the immediate vicinity of the wind monopile installation. There's also, as I mentioned, a lot of planning that goes into export cables, and there's a few kind of considerations that go into export cable sites, as well as routing and siting in the offshore wind area. Oftentimes the onshore land or point of interconnection of these export cables are constrained due to access points on land that are publicly available and are close to energy storage facilities, or maybe even some different port areas. Also, there's geologic constraints, such as the developers want to avoid hard or extremely soft bottom where practicable. It's difficult to bury a cable under hard rock bottom. And there's also what is known as cable burial risk assessments. These identify potential conflicts with different marine users, including trying to avoid heavily fished grounds and try to come up with ways of mitigating interactions with fishing gear and seabed composition. So I have a snippet here from one of those cable burial risk assessments on the bottom right here, where you show the gear type where that a fisheries may use. So this is one of the deepest kind of types of gear that may be used, such as an hydraulic, clam dredge that goes into, 10 to 20 centimeters below the sediment surface. And they identify the penetration depth of these gears, the area that it's used, and they try to avoid, inadequate burial in these areas. They want to try to bury it as deep as possible to avoid any interaction with fisheries gears. The target burial for most projects is 6 feet. However, the range can sometimes be 3 to 12 feet. And there's a variety of factors that go into this. As I mentioned, if there's a lot of hard bottom, sometimes they may not be able to interact with the cable to a certain depth. They may not be able to bury it adequately. There's also different tools that are used for cable burial. You can see here these images on land of a cable plow that simultaneously drags the cable behind it. You can see here in the picture on the right. So it simultaneously lays the cable and buries it once it's towed to land. And as I mentioned, there's a few different kind of areas where there's inadequate burial of the export cable, and in areas where you can't reach that target depth of 6 feet, such as in areas of severe slopes, crossings with other types of cable infrastructure, as well as considering the proximity to offshore wind infrastructure and the type of soil and bedrock that's present, you may require additional artificial armoring of these inadequately buried areas along the cable route. So here I have pictured of a potential variety of different types of concrete mattresses that may be used to cover these inadequate burial sites, rock bags, concrete half pipes. So there's a variety of different mechanisms that these developers can use. But as you can imagine, there's a lot of concerns that go into this artificial armoring introduction from both an ecological and marine user standpoint. So, for instance, there's concern that there may be a lack of nature-inclusive designs of these artificial structures that are introduced over these cable sites that are not able to be buried. For instance, there's been evidence over time in other projects of where just general concrete mattresses with low interstitial space don't really benefit the environment. They don't really increase species richness or abundance. There's been alternative designs such as this eco-concrete mattress, which has been developed in Europe to try to increase engravings, interstitial space to promote epifaunal growth of a variety of different, invertebrates, which could then potentially attract other demersal and fish species. However, there's still some questions that remain about its applicability and its feasibility in terms of bolstering species richness. There's also concerns about changing the seabed ecology. If you're introducing, hard bottom and sand structures, sometimes species need that sand structure to survive or reproduce, et cetera. You can imagine introducing potentially some hard structure on sandy environments, potentially where scallops are. There's one concern that, this could attract predators that could then change the predator-prey dynamics between scallops and their predators. It could also cause snags with mobile gear fisheries, especially trawlers, dredges, especially if they're not identified and fishermen are unaware. There's efforts to make these areas aware to fishermen, but there's no kind of centralized repository for this. There's also concerns that introducing hard bottom may preclude fisheries independent surveys, such as the variety of different Northeast Fisheries Science Center and NIMP surveys, and potentially even state-run resource assessment surveys, such as the DMF survey that occurs in the spring and fall. And in fact, I've already, been in contact with Steve Wilcox here at DMF about, trying to avoid some of these hard bottom areas and notify him to respond accordingly with their own assessment survey. Another point I want to mention too, there's also introduction of hard structure through boulder relocations from the cable construction process. Pictured here is a kind of boulder sled device that will be towed in the route of the export cable, and it can kind of shovel and uproot these boulders to the sides, to the waypoint. There's also different types of gears such as jet sledding that can also help remove boulders, and even these kind of grab devices. So there's a variety of different techniques that developers may use to move boulders. And there is currently no boulder like relocation or mitigation plan, which has actually been a concern among us as well as our counterparts at the Office of Coastal Zone Management and NOAA, because Developers are currently not required to characterize where and when they move these boulders, what types of boulders they're moving, like in terms of size and the extent, which you can imagine, can cause hazards at sea for some fishermen if they're not adequately located and they're not on, let's say, chart plotters or digital platforms. So there's actually been some work done by our Office of Coastal Zone Management, as well as with DMF, in terms of recommending a boulder mitigation plan that requires the developers to characterize where they place these boulders, how they place them, and identify affected habitats associated with this plan. So we're trying to do that so that way it's installed in a lot of these construction operation plans by developers. As I show here in this text, you can introduce safety risk if there's not any plan in place to mitigate these boulder relocations. So now I'm going to go into the status of the Southern New England areas. I know some of you are probably familiar with interacting with the South Fork and Vineyard Wind projects. These are the two kind of projects that have been installed or partially installed. So you can see here in these green shadings, just south of Martha's Vineyard, we have Vineyard Wind highlighted in green. That's the largest area that's been undergoing construction. And then South Fork Wind is on the Rhode Island, Massachusetts border, about 10 nautical miles south there. And South Fork Wind has completed all of its installed turbines. Vineyard Wind still has, a lot of their towers that need to be constructed, but they installed most of their foundations. Revolution Wind, Sunrise Wind, and New England Wind are the next three types of lease areas that will be developed over the next year or so. They just had their record of decision approved by BOEM. And currently all other projects under various phases of environmental review and siting. But if the permitting process is stays on track, they're expected to be constructed by 2028. So over the next 3 or 4 years, all of these Southern New England areas, if everything goes as planned in terms of environmental siting and review, then we will likely see them be partially or fully developed by 2028. And I just want to focus in on the current status of Vineyard Wind a little bit more here to give everybody an idea of where these monopiles are placed and what turbines are placed. So here I have an image showing you an inset of Vineyard Wind lease area. You can see the foundation locations on this inset map. Currently, there's only 47 monopiles installed out of the 62 planned turbines within Vineyard Wind. Of the 10 wind turbine towers that have been installed, 5 are producing electricity, which is roughly powering around 30,000 homes. 20 have these transition pieces, which you see pictured here, along with their monopile foundation. And then 17 currently have no transition pieces or towers in place. You can just see here the monopile foundation itself in the bottom left. And it's expected to power 400,000 homes and is currently owned by Avangrid. South Fork Wind is much smaller. It has 12 turbines that are generating electricity. And instead of powering, Massachusetts homes, it's actually going towards New York. And it's currently able to power around 70,000 homes, currently owned by Ørsted and Eversource, and was the first large-scale commercial wind farm to be producing electricity in the U.S. So that was some news as of late last year. So I also just want to transition now from the construction updates, and you kind of all have seen, what goes into offshore wind development. And I want to just highlight some uncertainties and how these uncertainties have actually led to some fisheries compensatory mitigation by Vineyard Wind and South Fork Wind. So here I have a kind of a network plot showing you 4 kind of different programs that have different uncertainties with offshore wind development. So here in red, I have fisheries management. Green, I have fisheries operations. Gray, I have offshore wind development and its impact on fish movements and habitat, as well as shoreside and support businesses in orange. And these are not all the uncertainties that are a concern within the offshore wind realm, and in accordance with each of these kind of different sectors and groups. However, I just want to mention, these are just some of the more important ones that we've heard about through many different stakeholder engagement sessions, and the fisheries working group sessions. So in terms of fisheries management, some of the major concerns with offshore wind development is potential changes in fish production, biomass, and distribution from introducing this hard structure It can change the potential hydrodynamics as well as nutrient mixing, maybe changes to fish attraction or avoidance, especially during construction and operation periods. Fish may respond differently. There's also potential for differences in fisheries accessibility and co-use conflicts among gear types. You see in the fisheries operation phase, safety is a concern, both in terms of dragging nets, maybe due to artificial hard structure, but also navigation interruptions. There's some evidence from the National Academy of Sciences that there could be some Doppler effects that could be introduced from wind turbine construction that could affect, radar capacity. So if fishermen are feeling unsafe within the environment, they may want to fish in the vicinity of the wind farm, especially those mobile gear draggers. And this could end up causing maybe congestion within the vicinity of the wind farm area, could cause greater conflict among different gear uses, such as fixed versus mobile gear fisheries. There's also concerns from fisheries independent survey operations. So as I mentioned, NIMP surveys are a concern in terms of their continued operation within wind areas. There also is other fisheries operations concerns, such as there's a clear lack of insurance liability that what we've heard from different stakeholders. There hasn't been really any clear plans for if who's at fault if there's any type of collision with offshore wind infrastructure, or who's at fault if there's any damage of gear. There are current gear programs in place to compensate fishermen if they damage or lose their gear from offshore wind infrastructure. But again, if there's other types of hazards that are a byproduct of this is something that is kind of a black box. And then there's also some, obviously I touched upon noise impacts from the pile driving that could cause avoidance behavior in many fish species. There could be electromagnetic field impacts, especially on electrosensitive species such as sharks and elasmobranchs, and changes in the distribution of fish, maybe from attraction or movement through wind farms. So these are just kind of some of the major uncertainties that I'm going to be touching upon in the next few slides in various different ways. I'm going to try to touch on each of these components. So as I mentioned, there's been a lot of compensatory mitigation packages that have been in agreement with the currently approved Southern New England wind areas and those that are constructed. Currently, Vineyard Wind and South Fork Wind have compensation for fishers. They vary in terms of the size of these different, compensatory agreements between the Commonwealth and the developers. And there's a variety of different reasons for this. Some of, Vineyard Wind, for instance, assumes that no fishing access was going to be occurring throughout the entire 25-year operation of the Vineyard Wind site. Whereas South Fork Wind assumed that fishing would almost, occur as business as usual throughout the operation of the wind farm. So therefore, they thought that the construction aspect, where there may be temporary exclusions in certain areas that could cause loss or access to fisheries operations, was likely the major source of impact or loss within their small wind farm just south of Rhode Island, Massachusetts border. And there's a lot of data that goes into these compensation plans through fisheries economic exposure reports. But each of these developers use different assumptions in terms of, assuming, let's say 50% of fish avoid pile driving activities during the first few years of construction. That's one example of assumptions that some kind of companies may make. So there's differences in assumptions that go into this as well. And I'm going to focus on the differences between these compensation programs, as well as their eligibility requirements that are overlapping between the two. And I think it's important to keep this in mind as I head into some of the next few slides. So, for example, South Fork Wind is owned by Ørsted. Some of their eligibility requirements for fishermen to receive any benefits, they have to show an impact or loss from offshore wind developments. That could be due to erroneous interactions with offshore wind vessels during maintenance operations. It could be due to construction. However, they're required to have consecutively fished within the South Fork Wind lease area, at least within at least 3 years before their notified impact or loss. If they're then eligible through the South Fork Wind program, they receive a one-time payment. And currently, the South Fork Wind compensation program is available for hiring commercial vessels. In contrast, Vineyard Wind, throughout the entire operation phase of their lease area, assumes no fishing would occur. Hence, that's why they have such a larger amount dedicated towards compensation. They also require some baseline period of fishing activity from 2016 to 2022, where fishers were actively fishing within the lease area prior to construction. So fishermen can, as long as they can provide some sort of evidence during the baseline period that they were in the array, such as VMS or AIS data between 2016 and 2022, they're eligible. And they can be eligible for potentially a series of 5-year payments throughout the operational lifetime of the Vineyard Wind project. So if they're eligible for the initial round, which the application is currently, in its ongoing window, the fishers can receive payments every 5 years as long as they're actively fishing throughout the entire operational period of Vineyard Wind's lease area, and it's available only to commercial vessels. So it's not available for hire vessels like the South Fork Wind Plan. And then some kind of criteria that overlaps in terms of eligibility for these compensation programs is, they must have home ported vessels in Massachusetts, some type of valid state or NOAA fisheries permit, some evidence of fishing in a baseline period prior to construction before each of these lease areas came online. And currently, the claims and eligibility review is not done by the offshore wind developers themselves. It's actually done by independent third-party administrators. So given the lack of kind of cohesion of a lot of these, different types of eligibility requirements and what goes into the assumptions of compensation, there's an initiative by the 11 states from North Carolina to Maine to establish a regional fund administrator for fisheries mitigation, which can provide financial compensation or economic loss from offshore wind development off the Atlantic coast. So the reason why the states are getting together for trying to come up with a centralized plan for mitigation and identifying one independent regional fund administrator is that there's currently no mandate federally for developers to have a financial mitigation plan for fisheries. So it's been kind of left up to the states to negotiate with each individual developer and each project to negotiate, what the funds will be used for, whether it's direct compensation or towards other types of funds, such as navigation funds or innovation funds. So it's really been a kind of a messy process. And, one way of trying to make it easier for fishermen to apply is having one centralized and transparent initiative and independent regional fund administrator to review claims and eligibility. And there's going to be a lot of stakeholder engagement that unfolds as part of this process throughout the next 2 years. So once a regional fund administrator is identified, there's going to be a design oversight panel that will then be comprised of offshore wind developers, state agencies, and fishermen reps that will then guide the RFA on eligibility and compensation requirements. So I also want to mention the non-direct kind of compensation agreements that the Commonwealth has agreed to with, some other types of companies and lease areas. So, for example, through Ørsted's programs, such as South Fork Wind, Revolution Wind, and Sunrise, the Commonwealth also negotiated, in addition to direct compensation funds, Ørsted agreed to set aside money towards navigation and safety funds, which includes upgrades to navigational equipment such as radar AIS systems, as well as dedicate monies towards professional training opportunities, such as potentially giving vouchers to mates for training for, let's say, captain's licenses. There's also other experiential learning opportunities that come out of this process. So in total, there's been about $1.3 million just with Massachusetts alone that has been dedicated towards these efforts. Only $300,000 is available because South Fork Wind is at financial close. It's already under construction, but further money should be coming over the next 2 years once Revolution Wind and Sunrise become constructed. There's also another fund that was agreed to with Vineyard Wind. Many of you may be aware of this, where DMF chairs this $1.75 million fund that we currently have. And this Vineyard Wind Innovation Fund can be used to promote the coexistence of fisheries and development of offshore wind in the Northeast Atlantic. So it's not specifically just for Vineyard Wind lease area, it's for all offshore wind development in the Northeast Atlantic at large. And there's a few different kind of branches of where these funds could be useful. They could be useful towards promoting safety, technology, innovation kind of gear or funds that could be used, let's say, towards personal flotation devices, enhancements with increased AIS and personal locator beacon access that could be used towards sea survival training and captain's license programs, as well as upgrading vessel trip report logbooks. There could also be monies used towards testing alternative gears and artificial habitat testing, such as maybe testing out automated squid jigging. These monies could be used to start up like a pilot program to examine that. We've also heard from other fishery stakeholders that there's, other kind of aspects of this program that could be useful, such as, promoting marketing seafood to help the seashore dealer sales and fishery sales. Maybe we can introduce some high quality processing techniques to increase seafood value as part of that program. And there is always a need for increased maybe radar and technological upgrades, testing these different types of new radars to see if they're more compatible within offshore wind development areas. So there's a lot of different aspects that can come out of this Vineyard Innovation Fund, and it's guided by 9 fisheries reps. So DMF chairs it, but there's a lot of fisheries reps that guide that process in terms of prioritizing where these funds should be in place. Another concern that I mentioned, is uncertainty with offshore wind development and concerns was the interactions with federal fisheries surveys. So there's actually a study done by Elizabeth Mithrada that identified 4 main ways in which offshore wind development could interact with fisheries independent surveys. One of those is preclusion, where you could have displacement of survey vessels by the introduction of wind infrastructure. It may not be safe to navigate through those areas. There could also be impact statistical survey design. If they're not able to access these areas, they may not be able to use the same randified or stratified random design within those surveys. There could also be changes in habitat and structure directly from the wind farms that could kind of be a confounding in terms of implications of looking at trends associated with stocks over time. And there's also just the issue of practical sampling that NIMS has identified, where if they're not able to access these wind energy areas due to safety concerns themselves, they could be required to navigate around WIAs or wind energy areas and increase transit time and sampling time. So the results of these impacts, if they're unable to be resolved, one of the main concerns we've heard from the fishermen is that they're worried about uncertainty in fisheries management, potentially if there's no mitigation strategy or mitigation efforts that are in place. There are efforts by NOAA and BOEM to have a federal survey mitigation survey strategy to maybe standardize different gear types and vessels to replace these surveys. As you can see in this map on the right-hand side, this is the Gulf of Maine draft and final wind energy area. The final wind energy area has been established by BOEM as of a few weeks ago. And it's a striped area, and there's at least 10 to 11 different types of federal surveys that overlap within the potential for future wind development in the Gulf of Maine. So it is a main concern. Another potential solution that was identified by NOAA was that there are a lot of project level monitoring programs, both fisheries and habitat monitoring programs undertaken by wind developers in their respective lease areas. And there was actually a big study that did a synthesis of kind of all of these different projects that were currently underway by offshore wind developers to see if they could be a feasible kind of alternative to replace some of these independent fisheries surveys. However, there's a few kind of issues that were outlined as part of this study. So on the top right here, you can see that one issue is that the duration of these different projects or research monitoring programs varies. You can have just within 1 year, 15%, almost 50% of projects have less than 1 year, whereas the majority of projects have 2 years or are unspecified in terms of their duration. So the duration is not consistent among programs. There's also different types of species targets. And therefore, this requires different types of trawl gear, telemetry, different types of gear used to address their different objectives. There's no cohesiveness in objectives. And what this study ultimately found is that only 34% of current programs, research and monitoring programs, were consistent with any other regional or state fisheries independent survey. So the majority of these surveys currently underway are not compatible or feasible alternatives currently to a lot of these fisheries independent programs. There's also another concern that was identified, such as data sharing is often currently labeled as proprietary by many offshore wind developers. So it's even difficult for managers, and I've even heard some own fisheries liaisons that work for developers have a hard time getting that raw data because based on who they contract and consult with, they want to it's hard to get that proprietary kind of requirements released. So now I'm going to be transitioning into, I identified some uncertainties across various different aspects of fisheries and offshore wind. But now I want to kind of go into lessons learned from both a mix of laboratory and field studies in terms of various different phases of offshore wind development on fish and their associated habitats. And I'm going to be mainly focusing on lessons learned from Block Island Wind Farm in terms of these different studies that examine changes in fish distribution and behavior. So for those of you that are unfamiliar with Block Island Wind Farm, this is the first small-scale wind farm that was established and generating power as of 2016, just south of Block Island Wind in Rhode Island. These are actually spaced much closer, about half nautical mile apart compared to the 1 nautical mile spacing in the southern New England region. They're also smaller turbines. They're about half the size of the turbines that are currently being installed in southern New England. But there is a variety of different kind of habitat types and structure that spanned these different 5 wind turbines. And there's a lot of studies that looked at the construction and post-operation impacts of development on a lot of different aspects of benthic ecology and fish distribution, et cetera. So I just want to focus on one study conducted by Hutchinson et al. That looked at the ecological impacts of offshore wind construction, both in the turbine tower structure and directly in its vicinity around the foundation on the sediment surface. What the study found that 4 years post-construction is that there was, the greatest amount of change occurred in terms of species composition directly at the footprint of the jackets. There was really no strong gradient or changes in sediment size or species, kind of assemblages beyond the 30 to 90 meter mark across any turbine. So it's very localized in terms of these post-operation impacts. What they did find is that there was some benefits with the Block Island Wind Farm in terms of increasing epifaunal growth, such as blue mussel growth. That biomass did increase, which then attracted some other predators such as barnacles and crabs. And ultimately, in some turbines, black sea bass appear to be attracted to some of these turbines. However, I just want to emphasize that species composition differed among turbines, primarily due to differences in hydrodynamic effects, as well as the underlying kind of sediment and biotope characteristics that were around each turbine. So these results were not consistent among each turbine. And we can see that based on some images from the study where when you look at different types of sediment types, there's different predominant species in the baseline period, which was around 2010. That's when a lot of the baseline studies started to get an understanding of what type of species were abundant before construction. For instance, in turbine 1, we see that over time, during year 3 post construction, we saw a transition from polychaetes being dominant to a lot of sessile invertebrates, such as barnacles and blue mussels being dominant. You can see here pictures on the right showing that progressive growth from 2018 to 2019. However, even with the same kind of sediment type, turbines 3 and 5 tended to have differences in composition where polychaetes were primarily dominant as well. But, something that was interesting is that, when you compare the baseline period, the dominant species was not the same 3 years post-construction across any of these turbine types. So there was a change in a lot of the species assemblages or the dominant species that were represented. And one of the main reasons that turbine 1 was actually thought to have greater epifaunal sessile invertebrate growth was that there was actually lower hydrodynamic energy. You could actually still see construction tracks from cable installation and some other features that were still present 3 years post-construction that were kind of erased from currents and the other turbines. So this makes partially explain why there was some differences in invertebrate composition, allowing maybe a rapid change in ecological succession in that turbine one compared to the other turbines where there's maybe more disturbances in place. And in turbine one, given that there was a lot of this sessile invertebrate attraction and growth, it also tended to increase the black sea bass abundance in the vicinity. However, it remains to be seen whether or not this actually is increasing the production of black sea bass. I think that will take many years to quantify. So, the attraction versus avoidance of many fish species on wind infrastructure has yet to be answered. And there's also a study conducted by Wilbur et al. In 2018 that looked at winter flounder abundance within and around the Block Island wind farm. You can see here on a map, they had different transects looking at the affected areas of during wind farm construction and operation. They also had reference sites north of the Block Island wind farm and further to the west, at least a couple kilometers away. And what they found was that during the fall, when there was pile driving that occurred, so pile driving was only occurring in the fall for Block Island wind farm, there was an immediate kind of lowering of winter flounder abundance. You see a decreased abundance trend compared to different phases. Even before construction occurred during that baseline period, abundance was higher. And then once turbines were installed and operation was underway, we actually in fact see that there was the same, if not greater abundance of winter flounder compared to pile driving and compared to the baseline period compared to the reference sites. And then when you look at other seasons such as winter and spring across these different phases, such as turbines installed or operation or cable laying versus operation, we see kind of similar abundances of winter flounder during the installation and operation or cable laying phase compared to the reference sites. This was suggesting that there may not be kind of large scale changes in winter flounder abundance during other non-noisy phases of operation and construction. And there was other flatfish that were monitored as part of this study, not only winter flounder, but summer flounder and window pane. And they appeared to respond, differently to pile driving. There apparently wasn't as much of a difference in terms of the baseline period versus pile driving and that reflection of window pane and summer flounder abundance. So this all goes to show that certain species maybe more sensitive to sound than others. And there's just a lot of uncertainty on a species by species basis on how they respond to these noisy interactions. There's also a study looking at pile driving interactions with black sea bass that was actually one of the more realistic that you could imagine taking place. So there was actually a pile driving study conducted by Aaron Mooney's lab at the Woods Hole Oceanographic Institution, where they looked at pile driving effects in a harbor across different distances. They had 4 different site distances of where they looked at before and after effects of pile driving activity on average black sea bass count. And they used beta underwater videos to track these counts of black sea bass over time. What they found was that in the near field sites within around 500 meters or less, after pile driving occurred, there was a much lower abundance of black sea bass, of juvenile black sea bass. However, there weren't as many differences noted a kilometer away or higher from the pile driving source. So what this suggests at the near field site is that juvenile black sea bass are avoiding this area when pile driving activity occurs, likely due to avoid the noise impacts. They also observed more sheltering behavior of black sea bass the closer they were to the pile driving site. And they did this through some cage studies where they looked at the position of black sea bass, and some of them were getting closer to the benthic environment than those that were not exposed to the pile driving noise. So this is just current research that's unfolding. This work has been presented in various formats, but is on its way to publication. Another aspect that I touched upon was the potential for electromagnetic fields affecting the behavior of different type of electrosensitive species, such as elasmobranchs and even potentially lobsters. So here's a schematic that shows the EMF, like a conceptual diagram of the EMF signal across different cable burial depths, as well as different anchoring environments. So EMF is the EMF field is a byproduct of that electrical current that's being transferred through these export and inter-array cables within the offshore wind farms. And the electric field itself is contained within an insulated sheet within the export cable. There's no electricity leaking from these cables into the environment, but an electric field is actually induced by the magnetic field. So the stronger the magnetic field, the greater the electric current that's generated as a byproduct of that magnetic field. And there's a lot of different factors that can influence the strength of these different EMF intensities. The type of cable, for instance, alternating current has lower types of EMF generated compared to direct current. It also depends on the burial depth. The greater the burial depth, the less exposure EMF is to animals in the above surface environment. There's also impacts based on the intensity of electricity generated at any given time. The more electricity generated by a wind farm in unit time, the greater the EMF signal could be. So there's a lot of different factors that go into the EMF that's emitted. However, there have been some studies based on other kind of electric current projects from just transferring undersea electric current from non-energy programs, non-offshore wind programs. There's been evidence that there's been electric fields that mimic prey bioelectric fields that these predators such as Lasembranchs use to identify prey. So there's a lot of kind of realistic concerns of where these low EMF intensities could potentially interfere with the not only navigational behavior but also the predator-prey dynamics between these electrosensitive species and their prey. There's a lot of studies. There was this one study actually conducted by Cressy et al. In 2023 that examined the larval cod and haddock behavior across different EMF signals. So they placed a lot of larvae, which has been known to be one of the phases of cod and haddock that could be electrosensitive. In these different raceways, they had on the left side of the raceway a stronger EMF signal versus the right. And they were comparing average speed and acceleration as well as max speed and acceleration between two different types of behavioral groups of this larval cod and haddock across a 2-day trial. What they found is that in the exploratory group, which were more active and more mobile, there was no difference in speed or acceleration between the control and exposed EMF group. However, in the treatment group with the higher EMF exposure for the non-exploratory cod and haddock, there was some evidence of some slower speed and acceleration. Again, this was within a laboratory study, so it remains to be seen whether or not this is what you would expect in the field. There were realistic EMF signals that were a part of the study that what you could expect if there's an exposed area of an export cable, for instance. However, it is an uncertainty in the real world, so I just want to emphasize that. There's also been some studies that have looked at EMF effects on little skates. There's actually a export cable in Long Island Sound that transfers energy between Long Island, New York, and Connecticut. And this study used acoustic receivers. They made acoustic receivers that were able to be transfigured in a 3D kind of array over this kind of trap that they made by wood. So the researchers, what they did is they examined little skate movement, 3D positioning, to look at EMF impacts on speed, distance traveled, and frequency of turning angles of these little skates within these wooden traps on the bottom. They did this over the course of 12 to 24 hours, and they had a treatment site that was directly over the cable, as well as a control site over a kilometer away. And they monitored the 3D positions of these little skates. And there was actually a departure from Earth's background field. As you can see here in these plots, I have the magnetic flux density on top and the electric field on the bottom. There was pretty high departures when you were within about 20 meters or so of the export cable. So you can see that there was definitely some elevated EMF signals compared to Earth's magnetic field. What they found as part of this study is that overall they had control and exposure treatments across multiple different periods. And they looked at different zones of different EMF intensities along the cable route. So zone 1 had higher magnetic fields versus zone 2. So that's just something to keep in mind. But once the exposed group was subjected to EMF signals within these cage experiments, they tended to exhibit a greater affinity towards being lower in the water column, more towards the sediment surface versus those that were in the control group. They also tended to have a greater frequency of more tortuous and large angles, signifying that they were maybe more confused or exploratory within these experiments. And you can see here, based on these bottom plots, you can see there was very little overlap in a lot of the confidence intervals. So there was some significant interactions between that control group and that exposure groups. So what this overall indicates is that little skates, at least within that 5-meter proximity of the export cable, could potentially experience some significant changes in behavior. But again, there's uncertainties in how they respond to potentially real-world applications of EMF in the environment, such as within southern New England. So there's a lot of uncertainties still here. There's also hydrodynamic impacts that can be associated with an individual turbine. So, for example, there was a study that was conducted in the North Sea where a lot of offshore wind infrastructure has been in place for over a decade. And there's been some evidence of localized weakening and stratification of up to a weakening of up to 15% of stratification and potential currents downwind of the net current of the wind turbine. There's also potential for enhanced turbulent mixing, which was actually shown to potentially increase nutrient transfer between the benthos and the pelagic environment, and some modeling efforts were underway that suggested that phytoplankton and zooplankton biomass could actually increase 35% within these arrays. However, there could be downwind impacts such as altering of the pycnocline, where the pycnocline could be shallower the further downwind from the stream, but then there's also a deepening immediately around the vicinity of a turbine foundation of those pycnoclines. So a lot of questions in terms of actually monitoring these hydrodynamic changes and regime shifts, not only within an individual wind turbine themselves, but cumulatively across different wind turbine areas. There's actually been some studies that have shown that, just even the wind energy alone from a regional, mid-Atlantic kind of wind turbine farm could have reduced potential wind capture or wind energy potential within the North Atlantic, just because that wind energy has been absorbed so much from different downwind wind turbines. So that's something just to keep in mind. There could be a lot of unknown types of current and regime shifts in terms of hydrodynamics associated with offshore wind. So now that I've gone into the background and the impacts of offshore wind on the environment, I'm going to quickly go through what's next for offshore wind. The next step in terms of what's relevant to Massachusetts waters is that BOEM has identified a final wind energy area and potential lease areas for development in the Gulf of Maine. And BOEM went through, over the course of several years, a course of narrowing down potential suitable wind energy areas that got them down to this final wind energy area you see in green. This was due to a series of public engagement and commenting periods by not only fishermen concerns, but also government concerns such as those independent fisheries surveys. Other kind of protected species data sets were also included in natural and cultural resources. There was also wind industry interest in terms of where they would like to place offshore wind, as well as industry and operation efforts such as just the large scale navigational routes. Are those going to be affected, and how can we mitigate those? So there's a lot of different considerations that BOEM used to try to narrow down to this final wind energy area in green compared to this call area, which is shaded in blue. And what BOEM did is they used this suitability model, which incorporated data layers that went into each of these 4 submodels on the right. They split the spatial kind of resolution of these different data layers down into around 10-acre hexagonal grid cells. And in the end, they end up using normalized data sets. So they were all on a 0 to 1 scale. So they were comparable. They weighted all of them. Each of the submodels were weighted equally. And they took the top 60% of those suitability scores among each of these grids to come up with that final WIA. So what this final WIA represents is about an 80% reduction from that initial call area. And since the draft WIA, which is pictured in yellow, when you compare that to the final WIA, it's about a 43% reduction in terms of potential development in the Gulf of Maine. And currently, this final wind energy area is around, has the capacity to produce around 32 gigawatts of electricity. However, this exceeds the current kind of goals, that 10 gigawatt goal of Massachusetts, as well as the 3 gigawatt goal of getting energy for Maine. So it currently exceeds the goals of a lot of New England states. And I'm not going to go into this too much, but there is a report by NCOS that shows the different kinds of data layers and submodels that went into the suitability model. Picture on the left here is comparing the larger extent, which is the draft wind energy area, versus the final wind energy area. The bluer the cells, the greater the suitability was overall in the model, and the further red it is, the less suitable it is for different interest groups. So, for example, when you compare the overall suitability to the fisheries submodel, particularly in Wilkinson's Basin area, this was a large area that had low suitability in the overall final suitability model that was reflected. You can see here it's blue. Over here, it's of low suitability for the fisheries industry and community. So, there's still areas to further deconflict offshore wind development in the Gulf of Maine. So what's next in terms of steps for the Gulf of Maine? So there's a proposed sale notice that was just released where BOEM identified 8 potential wind energy areas or lease areas of where developers could potentially bid and auction for by the end of this year. And as part of this proposed sale notice, there's going to be a series of public engagement opportunities over the course of the next 2 months. And BOEM is trying to understand, and optimize and the configuration of these lease areas, determine bidding credits, how those are evaluated. So for instance, there are sources of bidding credits such as developers can offset their overall final purchase cost by committing towards fisheries mitigation plans. So they can replace 8% of the monetary value with a fisheries mitigation plan. And they can also, for instance, replace 17% of that total purchase price with a workforce and supply chain plan. So essentially, they'd be diverting monies, just not towards the federal government itself, but it would be diverting some efforts and monies towards these different kind of bidding credit examples. And what BOEM is asking for is kind of, how these lease areas should be designed, what the spacing should be to reduce conflicts between marine users, between these wind lease energy areas, and also identify existing and effective uses. And there will be a final sale notice in summer 2024, where there'll be a mock auction that will occur from these potential lease areas, and then bidders will have a final lease auction occurring in late 2024. So floating offshore wind is going to be the kind of primary mode of development in the Gulf of Maine, because given that the depth of the Gulf of Maine on average is 197 meters, typically developers are interested in fixed type of designs that are fixed to the sea floor at distances below 60 meters. And there's actually only been 2 floating offshore wind farms that have been developed worldwide. So it's a relatively nascent technology. Pictured here is a schematic from Equinor's project in the North Sea, known as the High Wind Seas project. Each of these 5 turbines that are floating are consisting of these spar buoy designs, which is kind of like a monopile hybrid that floats. And they each have 3 different mooring designs and have a series of interarray cables that are connected to each other. And there's a lot of different designs in terms of how these foundations and cable moorings could look like. But as you can imagine, these floating turbine designs, when you include the footprint of the moorings, can have a much larger potential footprint and interactions with habitats as well as marine users within the environment, including fisheries gear. So that's one of these concerns in terms of how do you mitigate that. So I just want to show you that of what the potential options are for floating offshore wind. There's really no consistency of different types of methods being used. But on the bottom here, these are different types of mooring designs that are currently being evaluated by a lot of engineering firms. You could have a series of chain and rope that are attached to these mooring anchor designs. Some could be catenary, which could have more slack in them. Others could be taut. Others could have shared types of designs with a series of weights or non-weights. So there's no kind of consistency of these floating offshore wind designs yet. But something to note is that this catenary structure, which has the greatest slack in it and has the largest footprint, this has been the commonly used kind of formats in Europe so far for floating offshore wind energy. And the depth, or the kind of distance of these mooring designs can be up to 4 to 8 times the water depth of these moorings. So, for instance, if you have water depths of let's say 600 feet, and you need 8 times the water depth in terms of the length equivalent or scope equivalent of that mooring, that could mean that there could be one mooring line that could be over 3,000 feet from each of these floating wind turbine structures. So, it's really important for us to try to, identify these affected impacts, what this could mean for fishing, and without standardization in place, it's really difficult to forecast, what some of these impacts and affected areas could be, depending on the spacing of these turbines as well. So here's just a picture of where offshore wind could be going. There's different types of designs, such as dual floating offshore wind structures, or a trellis design, where you can replace a lot of the individual turbines themselves. But overall, there's a lot of uncertainty in terms of floating offshore wind. And I just want to kind of highlight that here, showing you some different schematics. And as you can imagine, there may be differences in exposure efforts of EMF for potential for entanglement of different fish species. For instance, if there's fisheries gears that get entangled within the environment, this could be introducing potential greater risk for marine mammal entanglement. If there's greater cable or in the water infrastructure associated with floating offshore wind, could be larger scale, maybe changes from EMF impacts. Again, these are all uncertain, but it's just important to keep in mind. And lastly, I just want to mention that there's a lot of different groups and databases that I have linked here that show you, what the current knowledge gaps and uncertainties are, how they're being identified among these different entities. And I encourage you all to use this Northeast Ocean Data Portal. It's been a wealth of information to look at all these different kind of data sets that BOEM used in their suitability model, and you can overlap that with current wind energy projects. And with that, I'll take any questions.
All right, thanks, Justin. It's past noon time, so if you need to leave, feel free to do so. If not, stick around if you have some questions, unmute yourself and ask them, or you can put them in chat. Pete DeCola asks, will you provide copies of these slides? Great presentation.
Yes, I can provide the slides for sure. Happy to do so.
Question, Gary, Ray Kane.
Go ahead, Ray.
Yeah, thank you, Justin. Great presentation. Maybe I missed it. Is there a time restriction? I mean, we spoke a lot about noise earlier in your presentation.
Yep.
My concern is you've got a lot of highly migratory species coming through that area. Is there a time restriction on when they can pile drive?
Yeah, that's a good question. There is restrictions in place that, for South Fork and Vineyard Wind, for example, they're not allowed to pile drive between January and mid-May, mainly due to avoid, North Atlantic right whale interactions. So they cannot pile drive during those periods. There's also like some efforts, I know, with South Fork Wind to use passive acoustic monitoring as well as acoustic telemetry, at least temporarily, to identify if cod are spawning in the area, to cease kind of operations until, cod spawning is done, over about a 24 to 48 hour period. They have to kind of halt pile driving there, or they should. So there are different kind of temporal periods of pile driving activities that should cease depending on the detection of different species that are in the area. But overall, it's been a hard line between January and mid-May, in terms of pile driving activities ceasing.
So a follow-up question.
Yep.
Who monitors?
So I know SMAST, UMass Dartmouth SMAST has some infrastructure like acoustic telemetry receivers, but it also, there's offshore wind developers that are funding, different contractors that are deploying these different materials. So I know NOAA has been involved in some of these efforts as well. So there's a mix of kind of different entities that monitor this.
Thank you, Justin. Great presentation. Thank you.
Thank you.
Dave Martins has a question. How long does the pile drive activity last for each monopile? Is it several days per monopile or one day?
It should take 4 hours per foundation. That's what we've heard from developers. So in theory, you could potentially have 2 foundations installed per day. Typically, that's what I've seen as the max amount per wind energy project. So yeah, it's a good question.
Other questions? I had a quick question. What is the loss of power going from the wind turbine to the station on land? Is there a major loss or?
Yeah, it's not a major loss in terms of like the cost. So they use like levelized cost of electricity. That's what the developers use. They look at that. Currently within Southern New England, AC is the predominant kind of export cable. It has minimal loss, negligible loss so far. And, that's, up to like around 50, miles offshore. I think at that threshold around 50 miles, there's some questions as whether or not it's more cost effective to go to DC, direct current. For floating offshore wind infrastructure in the Gulf of Maine, I think there's more eyes in the DC to try to reduce that loss along the distance of the cable.
All right, thanks. Bill Emerald?
Yeah, thank you, Gary. This was spectacular presentation. Very, very well done, Dr. Bopp. You have a wealth of information. I wish we had more time to sit down and talk this over. But my fundamental question is going to be about fishing activities and impacts. And I just was wondering, has anyone heard anything other than myself about the dead squid that washed up on East Chop? I've got a photograph taken by someone who was on the beach. And it's not that dead squid don't sometimes show up on our shores. It just seems like the location at East Chop and the time of the year when these animals are moving through that area, now that we have transmission cables running up and a lot of activity producing power offshore. It'd be nice if we had some way of monitoring these kinds of events starting now at the beginning, so that we have a log of activities that may be or may not be related to what we're talking about when it comes to fisheries impacts.
I haven't heard. I'm not aware of the dead squid on East Chop, so thank you for bringing that to my attention. But I agree with you in terms of being able to identify these different, like, let's say, like EMF impacts over time, especially now that construction has been underway and there's operation of wind energy itself in the Southern New England area. I think it's going to, that's definitely something that I know the Regional Wildlife Science Collaborative is trying to be more involved with in terms of understanding, all these different entities that are involved in these monitoring efforts, getting them to a room, getting them, having everybody be aware of each other and increase data sharing opportunities to where we can potentially get at some of those more like real-time questions that you're getting at, Bill. It's been a lot of work done by that effort. So I think, I think as the, construction goes underway and these, there's more power being generated, I think there's going to be a lot of opportunities to look at more of these potential real-time impacts, especially with, passive acoustic monitoring. That's really important, for not only, marine mammal identification, but as I said, like cod and some other species that are vocal in the area. So it's a question that I think, everybody's been reeling with, but, I'm hoping we're on our way to a solution here soon.
Okay, one final thing, with Ray on the line here with us and other DMF personnel aware of what we just brought forward, maybe in the near future we can start talking about a way to further this analysis and start putting together comprehensive history on what the impacts seem to be. All right, thanks again. It was really well scoped, Justin.
Yep, thank you.
Chris McGuire.
Yeah, thanks, Gary. Great talk, Justin. Sort of building on Bill's comments, I'm curious if you could say a little bit about what you think DMF's role is in the rollout of offshore wind, and whether or not there's an opportunity. I mean, there's a lot of great researchers at DMF, so I'm curious if you guys are thinking about engaging on some of these questions in particular and how you would make those decisions. So just curious what you think DMF's role is in this whole thing.
Yeah, no, that's a good question, Chris. So currently our role within offshore wind development has been, mainly evaluating the fisheries mitigation aspects, evaluating the data that goes into those fisheries compensatory agreements between the Commonwealth and these developers. We also do a lot of environmental review of the different, fisheries and monitoring plans, as well as trying to recommend mitigation of these, let's say, noise or or introduction of hard structure, et cetera. So that's the main role that DMF has had so far is mainly the employing the mitigation hierarchy, environmental review processes, and then, also engaging with the fishermen has been another big one, right? Hearing their concerns, and sharing some of these compensatory mitigation funds. But in terms of research, I myself have been interested in, setting up even some like laboratory experiments for, let's say, the EMF impacts on a variety of different species. BOEM has a list of identified electric sensitive species to where it could be useful to see in the lab, are these species affected or not by EMF signals? And those studies are actually relatively easy to conduct and relatively cost effective. The setup costs are pretty cheap, less than $50,000 to have those types of in-lab infrastructure. But in terms of other projects, though, that decision making, I think we're going to be dependent on a lot of other requests for proposals, call for proposals from Sea Grant or other institutions to have some different programs in place. For instance, we have DMF staff looking at eDNA monitoring in the Southern New England area already. That was funded through different partnerships with GMGI, and there's continued funding looking at Mass CEC funds for that. So it really depends on the funding opportunities that are in way in terms of which DMF can expand that research capacity. But that's a good question, Chris.
Yeah, and you and I have talked before. I mean, I'm certainly interested in finding those opportunities where we could work together on some of those as well.
Yep.
Pete DeCola asks, has Sandlands been studied for EMF?
Not to my knowledge that I'm aware of. Yeah, I'm not so sure on Sandlands themselves. That's something that's good to know. I think BOEM actually has them identified in one of those species to look at for EMF.
Yeah, that's good. We've asked them to do that, so I'm glad to know that that's happening. Cool, thanks. And one more question while I've got you. It looks like DC is going to be what we're using in the Gulf of Maine. Does that generate a bigger, smaller, same type of EMF pattern as AC?
It typically does generate a stronger EMF signal. So yeah, it generally does based on studies that I've seen. But it also depends on how many turbines are connected to that export cable, right? The more turbines you have generating power, the stronger that EMF signal could be. So that's also something to keep in mind. It's not just the AC versus DC, but also how much energy is being generated at one time.
So if there's a backbone heading out to the offshore wind areas, that will have a much larger impact than if the export cables are done project by project. If I hear you correctly.
Right. Yeah, potentially. That's a concern. But yeah, then spatially, I guess, right, you'd have one area if it was consolidated, in one larger kind of export cable cord. Yeah, so those are trade-offs we have to look at is, have more, corridor, like have less corridors with more consolidated energy being transferred versus, trying to avoid multiple different, corridors that have more interaction capacity with different species and users. So those are the trade-offs.
That's exactly what we're looking at for Stellwagen, for sure. Cool, thanks.
Other questions? I could take one more question, then stop for lunch. Anyone? Okay, great. Thanks, Justin. It was a great presentation. We appreciate it. And this will probably be the last presentation for the year until, the season until probably September, October, when all the field work is done. So have a good summer, and we'll see you later. Thank you.
Thanks, Gary. Thanks, everyone.